gun to measure the speed of, vehicle that is on the street. So basic principle, it seems like, first of all, that officer is holding the speed gun and he's here, it's staying in here, not moving, a stationary object. And if you use that gun, it seems like it measures quickly the distance to that object. But let's assume that this radar gun does not know where that object is. It only knows how far it's away. So this is the circle centered at this point in here. Therefore, radar gun only knows that object is around that circle, not where exactly, because all of this thing has the same distance. All right. And the next moment, this thing is bouncing back and forth. You realize with a little bit of exaggeration so that I can sketch it easily. It's supposed to be a circle, like that. Suppose he was here, actually in here, and this is a straight line connecting that, and suppose it moved to that position, B1. So this distance and the difference of the radius is actually the same, right? Because it's lined up in a straight line. Would you believe that the distance the object moved is actually the difference of these two radius? Fair enough? But suppose this object moved from here to there, right? And radar gun will say, at one moment it was here, at one moment it was there. It only has the difference of the radius, right? It recognizes the same difference of radius if it moves from here to there over the same time interval. You can see that the second one here moved a lot farther than this first one, right? Therefore, it actually moved a lot faster, correct? And this one is moved a lot slower. But the radar gun will give you the same measure. Okay? So it seems like what radar gun is really measuring is the distance of this radius of this object. Object is here, and you focus on the distance. Doesn't matter how you go from left to right. The radar gun is focusing on what is the rate of change of this radius if it is stationary here. Okay? If it is moving away from us, or it's depending on the direction of this thing, sometimes it gives a positive number if it is growing. If it's shrinking, it's going to give you the negative number. If it is 20 miles per hour, that means this radius is growing, so it's moving away from where the center is. If it reads negative 20 miles per hour, it means the radius is shrinking, so it's coming toward to where the gun is. Right? Make sense? So we want to apply this one into XY coordinate system. So that this is one of the settings they have. Suppose the police officer is down there, and his coordinate, this distance here, is y0. Seems like distance is a positive number, but if you turn that into a coordinate, it has to be negative y coordinate down there, right? And he's not moving, he's just staying there. This is the actual road, and the car is moving over there to that direction like that. So the location of this car relative to this origin can be represented with x coordinate itself, right? So it's moving to that direction. And x dot represent speed of this object, right? If it's moving to that direction, do you think this x dot is a positive or negative? Positive, right? This is a positive direction of increasing. If it's moving to that direction, our definition of x dot is supposed to be a negative number, things like that. So this is not moving. So what radar gun is measuring is the distance from here to there, right? Here's a c. So c is also a quantity that changes with respect to time. If this guy is moving to that direction, do you think c is increasing? This is not changing. If this is here, if it's moving over there, did c increase here? Yeah, so c dot is probably positive as well if x dot is positive. Things like that. All right. Y0 is not changing. X is the quantity is changing. We have to relate this x with c such that we can figure out the functional equation on the rate of change, right? So what is the relationship between these two? X and C. What are you going to use? Right, right triangle. Right triangle is the key. So the famous theorem, right? What is it? Right. So what is the c squared? Is that just seems like the hypotenuse, right? So that the other one is x squared, and the other one is y0 squared, right? And I use y0 to indicate that that's actually not function. It's just a number. Right, right. That's the distance. So it's actually a negative number, remember? Or you can use a positive number. Whenever you need a coordinate, you have to use a negative number. But since it's a squared, it doesn't really matter. All right, so that's the equation. And what do you do now?
Figure out how far it is from the car at the initial, and then how far it is at the
Right. That'll give you the relationship in here. But usually, once you have functional equation and quantity, and what is the next thing we usually do? Right, solve for something. What is that something? Not C and not X. That will be a pre-calculus problem. This is calculus class. And what do we do? Rate of change. That's what we care about. Rate of change. How do you enter rate of change? I don't know why you said the zero. I would take the derivative first, right? Yeah, derivative first to enter the derivative. So what is the derivative of left-hand side? 2c, right? To the first times c dot, right-hand side, 2x to the first times x dot. How about this one? 2y0 to the first times y dot. That will be all incorrect, right? This is incorrect. What is this the correct one? Yeah, what is the correct answer to the second term? 2y? 0? 0? Anyone else? What's that, Judith? Times y, okay. Y 0 dot? Yeah. This is not correct. What is the correct answer?
that's a constant. So I thought
Yes, the constant you thought was 0, and that was correct. Okay? Make sure you get that part right. That's not changing. Y0 is not changing as time is always. So derivative is 0, right? So usually we have this information, right? That's rate of change of this distance is what the radar gun is giving to you. The speed gun is giving to you. So we know that information. Usually what we don't know is this one. How fast this car is actually moving in here, right? To the sidecar. Does that make sense? We don't know if it is a constant. The speed of the car is a constant. We don't know. Y is a constant. That's why it's a 0 here. This never changes. Yeah.
that's
Right.
where the car was originally.
Right.
That won't change.
So things are right. We're going to solve this thing for x dot because situation is that the radar gun, the speed gun will give you the information about how fast the C is changing. That's what this speed gun is telling you. And we want to figure out how fast the car is actually moving on that road. Right? So we're going to solve this thing for x dot. Is that right? So x dot. Do you see this 2 and 2 cancel multiplicatively? 2 cancel. Because it's 0. Then you divide everything by this x here, right? Correct? So it's x. So it's, I'm going to organize it like this so that it's easier for me to do something else later. Here's a c divided by x. Fair enough? Fair enough? All right. So if you know what this is a measure from the speed gun, and you know this distance, you have to know how far he is away from that origin to figure out how fast this one is actually moving, right? That's reality. But usually, police officers usually stay very close to the road and measure the speed of the object is pretty distant. So I'm going to enter slightly more concrete version. What is the c, according to the Pythagorean theorem, is root x squared plus y0 squared. Fair enough? And down there, there's x. That's quantities. There's no derivative. So I can replace that c with the square root of positive square root of x squared plus y0 squared. Correct? Then I'm going to do a little bit of a manipulation to explain what's happening here. I can put that x inside the square root after you square it. So if you put that underneath the square, it goes underneath it there. If you just put x there, that would be incorrect. If it is inside the square root, you have to square it back. All right? If it was outside, now you want to put it inside, you have to square it. Now if you distribute it, c dot, the measure from the speed gun, is 1, and this is 1 x squared divided by x squared, right? Divided by here y0 squared divided by x0 squared. I can put everything under square, so it looks like this. By continuity of the square root function, so if y0 is very small, so because he's right by the road, and x is relatively big, right? y0 is small, x is relatively big. So what is your rough estimate of this number? Big number or small number? y0 is small, x is big. This is of very numbers fairly small, right? So by continuity, what happened to this entire quantity? Pretty close to 1, right? Because 1 plus 001, square root of 1 plus 001 is pretty much 1. So if the police officer stay right by the side and measure the speed far, far away, you know, a lot more than this distance in here, that and then pretty much the actual speed of the car is because of c dot times this rough estimate 1 is pretty close to each other. So if you're right by the side and the car is far away, and if you use a speed gun, that measure is actually pretty accurate. But if you're significantly away from the road and this x is also very close, then the measuring will be very way off from the speed of the car in that side. All right? So that's what's behind this whole thing. All right, the book actually pushes this problem further. This police officer is not stationary there. This guy is actually approaching to that direction. He's driving, and at the same time he uses a speed gun, and this guy is also moving away from here. So if you carefully think about the whole situation, it's quite confusing. So you actually have to use something called Galilean relativity, allows you to interpret this one as if it is in a stationary object, and in here everything else is moving around. So with that one, doing some vector analysis carefully, bottom line is that, and out of all that, still the radar, the speed gun is actually measuring how fast this line is changing, length of this diagonal is changing. Same conclusion you have. So even if it is moving, the reading of the speed gun is still equal to the rate of change of this diagonal, the hypotenuse. So we're going to do the same thing, right? So here is a picture they gave you. And I want you to come up with, I was wrong. Explain all that. And I want you to come up with functional equation and quantities first. I'm going to go back to that. In there, they have additional description in there, so I have to copy in here as well. Entire problem. All right. The officer is driving north, and this one in here, that's a 30 miles per hour, right? to the north, and that's what this one says. So when you write down this information, you have to be careful. This is all embedded into Cartesian coordinate system, so you have to embed the positive, negative correctly. If it is moving to that direction, if that's origin, the coordinate is, I'm going to use the position of the officer, y coordinate there. Is that okay? Y coordinate. Is the y coordinate positive or negative here? Y itself, it seems like a negative, right? But if it's moving to that direction, and magnitude of the speed is 30 miles per hour, what is the correct number? Is that positive 30 miles we have to use for y dot at that instance, or negative 30 miles if it is going up like that? Positive is going up is positive. What about this one in here? I'm going to use the location of car with x coordinate. And if it is moving toward to the, how fast is it moving? We don't know. That's the whole question, right? How fast is it actually moving? But whatever that is, it must be a positive number, right? Because it's moving toward to that direction. C here, they said the reading is 20 miles per hour. They didn't put positive sign there, but it actually case the sign sensitive number. The reading is a positive means the C is actually increasing, right? Maybe this guy, the officer, is moving so fast, and this guy is moving relatively short. Think about the situation where they were like this. Officer moved so fast, went down here, almost this the other guy didn't move very much. So you can see it shrinks, right? So with that detailed information, we can determine whether C is increasing or decreasing, but it's not obvious that this is going that direction and that going that direction. C must be increasing. That is inconclusive. That is not sufficient information. But the reading says it's 20 miles per hour, and we interpret this 20 miles per hour as a sign sensitive information. They say 20 miles per hour, that means positive 20 miles per hour. If it is actually shrinking, they should have said the negative 20 miles per hour. All right? So we interpret this one correctly with the positive information. So we know C dot at that instant is a positive 20. Right? You don't have to think about, oh, is that positive 20 or negative 20? They said 20, it's a positive 20. All right? So, does it kind of make sense, the problem? So here is the quantity equation. So what is the equation on functional equation on quantity? C squared, right? It's the same thing. And here's x squared, correct? How about this part in here is not y0 anymore. It's actually changing as well, correct? Yeah, so it's a y squared as well. That's our functional equation on quantities. Then what is it we do after this? Functional equation on rate of change. So that's your exercise number 3. Did I get the number correct? Exercise number 3. Compute. What are we computing? Rate of change. That's right. Functional equation on rate of change. And let me tell you, answer is not the same as before. Seems like we're looking at the same thing, but the answer is not the same. Alright, was that okay? Left hand side C squared, if you differentiate it, you have 2C C dot, right? Right hand side you have 2x x dot. But this time y is not constant. Y is changing as well. The officer is moving. So you must have this 2y y dot as well. Everywhere there's a 2, so after you cancel it, this is the functional equation on rate of change. Make sense? Alright. So we usually have that information. C dot and x dot is what we don't know. So we're going to solve for x dot. So what is it if we solve for x dot? You have x dot is equal to c dot minus y dot. Is that right? If you subtract y dot from both sides, then you solve for x dot. So x dot is 1 over x c dot minus y dot. Alright? C is the distance at one instant, and c dot is how fast it was hypotenuse is changing. That's reading from the radar gun. And y is location of the police officer from the 0, 0, and is police officer's speed in there. All right, let me copy the problems there again. I'm showing it here. Okay, so at one instance that let's just think about at an instance there. I'm going to use a t0. So what is the xt0 is in that picture there? The location of the police officer there, right? It says 1/2 miles. So from there, this is 0.5. And this you have to be careful. Y of t0, what is that? Is the location of the police officer here, right? This is also 1/2, right? But 1/2 will be incorrect. What would be the correct answer? Negative 1/2 is down there, so you have to use negative 1/2. Important part, right? So we have that one, and we have that y, and we have y dot there. So what is y dot? Right, we have to get the C2. But what is readily available is when we're collecting there. Right. So what is y dot? How fast the police officers are moving, right? Is that positive or negative? Positive is going up. Is a positive 30, that's the magnitude. So we got y dot, y, and x, right? We have c dot. What is c dot in this problem? I was wrong about this 20. 20 is the reading, and 30 is how fast it's moving, right? Oh, I wasn't wrong. It was there, 20 miles. So I'm just gonna write that down. C dot t0 at that instant, the reading of the speed gun was positive 20, right? All you have to figure out is the CT0, right? What is CT0? At that instance, what is the hypotenuse? But that instance that it was 1/2 here, 1/2 there, and what is CT0? That's what we're looking at here, right? CT0 itself is a quantity of sides. So what is that by Pythagorean theorem? Square root of that plus square of that, right? So all together, that was square root of 1/2, right? So that's what that is. All right. Where did I get this one? From this triangle. CT0 is this is YT0. I was incorrect. This should be actually negative 1/2, right? That's the coordinate. But if after you square it becomes a positive. So identifying like this is important sometimes. So x coordinate at that instant t0 is positive 1/2. Y coordinate at that instant would be negative 1/2. So use the Pythagorean theorem, then it becomes squared. So it's both positive, positive. Is that what it is?
Yeah. Square root of 0.5 is
0.07. Like this? Very good. So that's that. So we got this number. We got c dot. We got y. We got y dot. We got x here, right? You plug it all in there to figure out actually how fast this car was moving. Notice here it requires this information, right? How, what was the distance of this car from this point to that, and his distance to that point. So we need this additional information to actually determine how fast that car was moving in that direction. However, if you stay close to that roadside and distance far away, you don't need that information. It's pretty accurate, like I explained it before. And especially if you're not moving, the officer's not moving in there. That's one reason why these officers are, right by this highway and measuring far distance away from. That's how you get this accurate measure. I think it's an excellent problem to make you think about physics and how this mathematics is involved to correctly interpret certain information. So I don't know the answer, unfortunately, but we have time. Will you go ahead and plug in all that and get an agreement to know what this number is? So let's finish that. So I think this number is pretty correct. 58 miles per hour. Alright, but the reading was, what was the reading? 20 miles per hour, right? Your speed gun says 20 miles per hour, but it was actually moving at a 58 miles per hour. Right? You're not going to get this much of a discrepancy, again, if you are very close to the road and this distance is far away, then this two number reading and the actual speed is not that different. And here it was actually significant sizes involved, so there's a significant difference in the measuring that. Fair enough? So this problem appears in 3, 4, 5, 6 in the